Chapter 5 is going to look at thermodynamics. So we're going to look at the energy now that's released during the course of a chemical reaction. We could use that energy to do things like perform work, right? Move our car down the road, or we could use that energy in the case of a fire, right? To warm, increase the average kinetic energy of the room, to increase the temperature of the room. Windmills, for example, being able to convert one form of energy into another using the wind's energy and then storing that energy. And we could also talk about something like sweating, right? When you exercise, you sweat, and then that water evaporates and taking heat with it and helping you cool down. A few important announcements. Chapter 4 and 5 homework will be due this Sunday, June 7th at midnight. The practice exam is posted, the study guide is posted, they're available on Blackboard. I also sent them out in an email. The midterm exam is Monday, June 8th. The exam will be available for 24 hours. It'll be on Top Hat, approximately 35 questions, some short answers, some multiple choice, some fill in the blank. I will provide you any needed equations as well as conversion factors that you would need and the periodic table of the elements. I'll have 2 review sessions. I'll have a Friday review session, 11 a.m. to 12 p.m. on Blackboard Collaborate. I will post the answer key shortly after that. That review session will be recorded and made available, and I'll also continue to hold the Sunday night review session as well. The Friday review session, I will focus on the practice exam. Sunday night, we can do practice exam questions. We could do homework questions. It's really up to you. So the one thing we didn't get to finish all the way and from lecture on Monday was oxidation reduction reactions, or redox reactions, right? I gave you the definition that oxidation is the loss of electrons and reduction is the gain of electrons. And I'm just touching upon that to just refresh your memory before we look at a redox reaction. And the important thing that I pointed out is that these reactions need to occur at the same time. If you have an element that's losing an electron, you need to have an element that's gaining an electron. There needs to be a transfer of electrons for a redox reaction. So if something's being oxidized, something in that reaction needs to be reduced in order for that redox reaction to occur. So here's a different redox reaction that we didn't look at yet, the reaction between HCl reacting with solid magnesium to produce hydrogen gas and magnesium chloride aqueous. And so let's take a look and break down this reaction in the ionic form to take a look and see if we can identify what's being oxidized, what's being reduced, where electrons are coming from, and where they're going in this reaction. And so here's the reaction. 2HCl aqueous react with magnesium solid to produce hydrogen gas and magnesium chloride aqueous. The ionic equation, remember to form an ionic equation, anything that's aqueous, right, will be written as ions in solution. So we'd have 2 hydrogens aqueous plus 2 chlorides aqueous. Magnesium is a solid, so it's not written as ions in solution because it's not an ion in solution, and because it's in its pure elemental form, the charge on magnesium would be 0. That goes to form hydrogen gas, so also not written as an ion because it's not an ion, and the charge is also 0. Magnesium is a group 2 metal, so it's plus 2 charge, and that's balanced out by 2 chlorides that are minus 1 each. So there's my full ionic equation. For my net ionic equation, I need to identify spectator ions, and if I take a look, spectator ions are ions that do not participate in the reaction. They go through the reaction unchanged. So chloride on the left and chloride on the right, right? Those are my spectator ions. Goes through the reaction unchanged. So my net ionic equation is 2H plus aqueous reacts with magnesium 0 to produce hydrogen gas, which has a 0 charge, and magnesium 2 plus aqueous. Now we can identify the redox reaction. So the reduction half and the oxidation half. right? So we said the reduction is the gain of electrons. And so if we look at the reaction, hydrogen starts at +1 and ends up at 0. So how must it do that? We must gain 2 electrons. So for the reduction reaction, hydrogen gains 2 electrons, right? So for the oxidation half, well, if hydrogen's gaining, magnesium needs to lose. And that makes sense because I go from magnesium 0 to magnesium +2. So how do I gain a charge of +2? I must lose 2 negatively charged electrons. So magnesium loses 2 electrons during the course of the reaction, right? It's oxidized. Hydrogen gains those 2 electrons. It's reduced during the course of those reactions. We can also confirm we get a change in charge as well. We go from +1 for the hydrogen to 0, and we go from 0 for the magnesium to +2 for aqueous magnesium ions. Clearly getting a change in electrons during the course of that reaction. So here's a question from you. It's a question right from the homework. Question 4.48. In the following reaction, how many electrons does each aluminum atom lose? We got a reaction between aluminum solid and platinum nitrate to produce platinum solid and aluminum nitrate. So if we break down this reaction, we see that we've got 2 aluminum, and again, aluminum is written as a pure element. So in the ionic equation, we would have aluminum, the 0 charge, that reacts with, right, we need to ionize anything that's aqueous. We've got 3 platinums. You might not know the charge on platinum, but if we look, every platinum has 2 nitrates associated with it. Nitrate has a charge of -1. So we got 3 platinums at +2 each. We've got 3 platinum nitrates where each platinum nitrate has 2 nitrates. So 3 times 2, we've got 6 nitrates. That reaction produces platinum solid, which again, it's a pure element, so it's got an oxidation state of 0. And I'm going to get 2 aluminums. Aluminum is group 3. It's going to have a charge of 3+, aqueous. And to balance out the reaction, I'm going to need to have 6 nitrates, -1 each. So look at the balanced reaction, and I need to figure out, okay, how many electrons does each aluminum atom lose? Well, they're already telling you that aluminum is being oxidized. It's losing electrons. So let's just focus in on aluminum. Aluminum goes from 0 to aluminum 3+. So how many electrons does aluminum lose? Well, to balance this reaction, right, I would need 6 electrons total over my 2 aluminums, right? So divide the whole reaction by 2. I would get aluminum 0 goes to aluminum 3+ aqueous plus 3 electrons. So aluminum is going to lose 3 electrons during the course of that reaction. In the previous reaction, and here's the next question, question 4.50. In the previous reaction, aluminum is what? Well, they already told you aluminum is losing electrons, and loss of electrons is oxidation, so aluminum is oxidized. Going back to the main reaction, right, we should be able to also break down this reaction in the half reaction for platinum, as well as identifying things like the spectator ions in this reaction. The 6 nitrates, they go through the reaction unchanged. Because aluminum is oxidized, we should also be able to identify that platinum must be reduced. So the reaction for platinum would be 3 platinum 2+. In order for that reaction to balance out, that must gain, right, 6 electrons to go to 3 platinum 0s as elemental platinum. 3 platinums, each gaining 2 electrons, 3 times 2, 6 total electrons for the reduction of platinum. And just a few rules to help that we've already kind of worked through the rules, but just to kind of identify each of the rules that'll help you assign an oxidation number in these redox reactions. And so anytime we're dealing with a pure element, the oxidation state, the oxidation number is always 0. So if I had solid iron or solid silver or gold or copper or aluminum, any pure elemental solid, the oxidation state is 0. The next rule we're also familiar with. The oxidation number of an atom, right, in an ion equals that charge. So, right, chloride is -1, sodium is +1. When we're dealing with oxygen, oxygen is going to be -2 in the exception that oxygen is bonding with itself like in hydrogen peroxide. But the oxygen we're going to work with, we're going to be very safe in assuming that the charge on oxygen is -2. Hydrogen, the oxidation hydrogen will always be +1. Halogens, right, will be -1 unless they're bonded to another halogen or they're bonded to oxygen. The majority of the time we're going to see a halogen, it'll be -1 charge. For a neutral compound, the sum of the oxidation numbers of the atoms needs to equal 0. If that compound is a polyatomic ion and it carries charge, then the oxidation numbers need to add up to the charge assigned to that compound. Two examples exemplifying this. So the sum of the oxidation numbers, right? If the compound is neutral, the oxidation numbers need to add up to that. So if I look at sulfur dioxide, for example, and I'm going to assign an oxidation number. So it's not an ion, but I can assign an oxidation number to this. If I break this down, this would break down into 2 oxygens that I know are -2 each, and 1 sulfur. Overall, the overall charge is 0. So if I have 2 oxygens at -2 each, the total charge there is -4. So the charge that I should assign, theoretically, to sulfur would be +4 in order for this to balance out and equal 0. That's the first sentence. The second sentence is the sum of the polyatomic ions, the sum of those oxidation states needs to equal the overall charge on that ion. So carbonate, CO3, 2-. I can do the same process. So carbonate, CO3, 2-. I break that down. I have 3 oxygens at 2- each. That's -6. So for the carbon, right, when I add those 2 together, the overall charge needs to equal -2. So the charge I would assign to carbon would be +4. -6 + 4 gives me that charge of -2 that I see assigned to carbonate. As we've already seen, we can break down reactions into each half reaction, the oxidation half, the reduction half. So here's just one more example, iron reacting with copper sulfate. So copper sulfate is blue in solution. I take that iron nail, I mix the 2 together, I form iron sulfate, and eventually, as you can see on the nail, I'm going to form copper solid, going to precipitate on the nail. So iron, pure elemental form, charge of 0. Copper, pure elemental form, the charge of 0. Copper sulfate as an ion in solution, iron sulfate as ions in solution. Let's break down this half reaction. So copper would be 2+ because my sulfate is 2-. Because sulfate is 2-, I'm going to be dealing with iron 2+. So for the oxidation half, right, the loss of electrons, that must be iron. Iron's going to go from iron 0 to iron 2+ through the oxidation, the loss of 2 electrons. If iron's the oxidizing half, then the reduction half must come from the copper. So copper 2+, aqueous must be reduced, it must gain electrons. So I'm going to gain those 2 electrons that iron lost to form the elemental copper, copper 0. So my oxidation half is looking at iron losing electrons, the reduction half is copper gaining those 2 electrons. And this sets up the most complicated aspect of redox chemistry, identifying the reducing agent and identifying the oxidizing agent in a reaction. The key to understanding this is the reducing agent is what causes the reduction. Right? And by causing the reduction, it gets oxidized in the process. Right? Loses electrons in the reaction. So the reducing agent, it is the reducing agent because that's what it causes. It causes the reduction. In order to cause the reduction, right, the gain of electrons, it needs to lose those electrons. It needs to be oxidized. Because it loses those electrons and gets oxidized, it allows, right, for the reduction to occur. It allows something to gain those electrons. And then the same applies for the oxidation agent. It's called the oxidizing agent because it causes the oxidation. Right? And in the process, it gets reduced during the course of the reaction. So because it accepts electrons, right, it gets reduced, it accepts electrons, that allows something to be oxidized, that allows something to lose electrons during the course of the reaction. So that's how we need to think about reducing agent and oxidizing agent. But I agree, they're always hard for people to differentiate the two, but it's what they cause in the reaction, not what happens to them. It's the reducing agent because it causes the reduction. It causes the reduction because it gets oxidized.